Greetings, everyone. Okay, this is more from 2.7. Number one, it says use the given graph to estimate the value of each derivative, then sketch a graph of f prime. I'm not going to do a whole lot here for you. This is just asking you to estimate the slope of the tangent line because that's what a derivative represents. So for instance, f prime of -3, go over here to -3, go down to the graph, and imagine the tangent line right through here. It's going to have a little bit negative, okay? If you go over here to -2, it's going to be 0 because the tangent line is horizontal. If you're over here at -1, it's going to be a positive number. Like if you gave this at say -1/2, then this is going to be larger than +1/2 because it's a steeper line with a positive slope. And then go over to 0 and give the value there. Go to 1 and approximate the value there. I think just plot those points and do your best to draw in a picture. That's all you're doing is approximating the slopes of the tangent lines at each of those values and then giving your best sketch. All right, number 7. The instructions for number 7 are on this page here. So before I turn over, it says trace or copy the graph of the given function. Assume that the axes have equal scales and use the method of example 1 to sketch the graph of f prime below it. Don't worry about the method of example 1. You can go back and read example 1. They're just sketching the derivative like we were doing in an earlier Desmos activity. So if we take a look here, remember when we're trying to sketch the derivative, I said a good place to start is at the horizontal tangents. This is a horizontal tangent at x equals 0, so the output of the derivative is going to have to be 0 at 0 because the horizontal tangent line here. Now, the way the graph goes this way, when we get over to the ends of the circle, the actual tangent lines here are not, the outputs aren't 0. I'm just highlighting what's going on here. The tangent line is going to be vertical at this point. So that means the slope is going off to either positive infinity or negative infinity, depending on what side you're approaching. So I'm just drawing some asymptotes that'll be in the graph of the derivative. Now, as we look over here, the slopes are all positive numbers on this side, and they're getting larger. If you start here at 0 and then slightly positive, more positive, larger, positive, more positive. So it's going off to positive infinity over here. And on this side, they're negative, slightly negative, more negative, more negative. So it's going to go off to negative infinity over here. I'll let you do the rest of the sketching, but that's essentially what's going on. Similarly, at 8, you're going to be doing the same type of thing. For 8, there are no horizontal tangents, but as we move for tangent lines along here, believe it or not, the tangent line is getting more and more vertical as we get closer to that. So you're going to have an asymptote for the graph of the derivative here. These are going towards negative infinity here because the slopes are all negative on this side. On this side, the slopes are all positive, so it's going to go off to positive infinity here. And then you can do the rest however you want. And you can stop the graph here. It looks like the slopes are getting smaller. I don't know if they're going to reach 0 or not. I don't know if this thing's going to keep laying down. But just do your best to do the rest of the graph of that one. For number 9, remember that any place the graph has a sharp turn, in 8 this is a sharp turn. Also in 9, these are sharp turns. The graph is not differentiable, so we're not going to have a slope at that point, okay? So there's no horizontal tangent line here because this sharp turn just doesn't exist. Neither does it here. All of these pieces in this graph in number 9, they're all linear. So the slopes, the derivative is going to be the slope of those lines at each of those intervals. So this is going to be a negative number. So the derivative on this interval here is going to be a negative constant. So it'd be horizontal, negative number here. Then over here, it's going to be a positive. And there's going to be a jump between the two representing the discontinuity for the derivative, or the fact that the derivative doesn't exist. Then back to a horizontal negative and a positive negative over here. Looks like these two pieces are a little bit more steep than these two, so this would be a little further away from the axis on these two intervals than on these two, would be a little closer to the axis. But again, it's all horizontal segments, some negative like these two, and some positive like those two. Number 20 is the next one on my list. And it says to find the derivative using the definition of derivative, state the domain of the function and the domain of its derivative. And we're dealing with y equals mx plus b. They want you to use the definition. If you have y equals mx plus b, you should know the answer needs to be m, because this is a line, and the derivative of a line is the slope of that line, which in this case is m. So, of course, this is going to be y of, are we doing this at a specific point, or just using just the definition? So it's going to be x plus h minus y of x over h. I'm not going to do much more work with you on this one. Y of x plus h is m times x plus h minus, I'm sorry, plus b. That's the y of x plus h part minus y of x, mx plus b, all divided by h. And then from here, just do the algebra. B minus b cancels. Distribute the m to each of these terms. The mx and this mx will cancel. You'll be left with m times h. Cancel the h's, blah, blah, blah. You know what to do. I hope at this point you know what to do. 34 is next on the list. So let's go see what 34 is all about. Looks like it's on the next page. It says, let P of t be the percentage of Americans under the age of 18 at time t. The table gives values of this function in census years from 1950 to 2000, so every 10 years. We just did a census, or this year was a census year, 2020, at the time of this recording, but the census is over. 2020 was quite a year, right, guys? Anyways, it says, what is the meaning of p prime of t and what are its units? Well, since it's a derivative in context, meaning in a particular problem, you do not, I repeat, do not say it's the slope of the tangent line. That's graphical, and we want contextual. We want to know what it means in the context of P of t being the percentage of Americans under the age of 18 and all that sort of stuff. So we're going to use the phrase, it's a rate of change. More specifically, it's the instantaneous rate of change of P. But what is P? P prime is the instantaneous rate of change of the percentage of Americans under the age of 18 with respect to time. Okay, so we always use, it's the instantaneous rate of change of the outputs. Here, P, the percentage of Americans under the age of 18 with respect to the input, which in this case is time. Okay, so this gives you the rate at which the number of Americans under the age of 18 is changing in these different census years. What are the units? The units of the derivative are always the output units divided by the input units. Because when we're talking about a derivative, when we take the derivative, it's the limit. I'll use p in this case since that's the problem. So it's p of t plus h minus p of t over h. The numerator here, this part is just the change in the percentage, okay? Whatever the change in P is, the output is percentage of Americans under the age of 18. So this up here is the percentage of Americans under the age of 18. Down here, this is the change in time, the T unit. So the units on this are the percentage of Americans under the age of 18 over years. Okay, it's really percent per year, percent over years. You don't really, in this part of it, need to put percentage of Americans under the age of 18. We're measuring it in percent, so the numerator is a percent, the denominator's in time, years specifically, so percent per year. Construct a table of estimated values for P prime. Remember, we did this all the way back in day 1 or 2 or something like that, from the beginning of the class. I know we didn't use P prime back then, but back then we were trying to estimate rates of change, estimate slopes of tangent lines, and we estimated those things with either for the tangent line with the slope of a secant line, or for an instantaneous rate of change, we estimated it with an average rate of change. So that's what you're going to do here. You're going to go on each interval from 1950 to 1960 and calculate the average rate of change. We can't do any better. We don't have a function that's giving us this data. We just have the name of the function and some values, some outputs of that function. So the best we can do is find an average rate of change to give us an approximation to the instantaneous. So you go from 1950 to 1960, and you'll put, you'll take the difference here, you'll take the difference here, which is 10, the difference of the outputs divided by 10. That's going to be your first entry. That'll be your approximation for 1960. Generally speaking, ladies and gentlemen, the way we're defining things, the derivative will not exist at the endpoints of a closed interval. Now we could define that like we did continuity being, function being continuous at the endpoint of a closed interval as using a one-sided derivative. We could, but we haven't, so we're not going to right now. So just leave 1950 blank. For 1960, use the average here. Then from 60 to 70, do the average rate of change on that interval, make that 1970, and just keep going all the way to the end. Just don't put anything for 2000. Let your last one be 1990. And then you're going to graph P and P prime, plot those points. If you're clever enough, you can have Desmos do it for you and see what's going on, and then sketch it or print it or whatever. And then how would it be possible to get more accurate values for P prime of T? Well, maybe we took the data every year instead of just every 10 years. Maybe we actually create a function that goes through all these points, and then we take the derivative, of that function. Maybe that function would be a good model. And any other way you can think of a more creative answer to that question. 35 is next. State with reason the numbers at which f is not differentiable. Well, the endpoints of closed intervals, as I was just talking about. So whatever value that is and whatever value that is, you can include those if you'd like. We gave 3 reasons or 3 ways a function can fail to be differentiable. One was if the function was not continuous at a point, then it's not differentiable. 2, if the function was continuous, but there was a sharp turn, then the function is not differentiable at that point. And 3, if the function was continuous, but there was a vertical tangent line to the graph at that point, then the function was not differentiable. So that's what we're looking for here. So over here at this value, there's a sharp turn, so the graph is not differentiable there. At 0, the function is not continuous. Left-hand limit doesn't equal the right-hand limit, so the function is not differentiable there. And it looks like there's a vertical tangent line happening. I don't know if it's right at 3. It looks like it's just to the right of 3, maybe, or maybe. Actually, no, I'm sorry, that's like 2.5. Yeah, I'm sorry, that's 3 right over here. Excuse me, misreading the tick marks. I thought maybe there was a tick mark under the blue line there. No, it's at about 2.5 because there's a vertical tangent line happening there. Lastly, number 41. It says the figure shows the graphs of f prime, and f double prime. Identify each of the following, identify each curve and explain your choices. All right, so it might be a bit of a challenge to figure out where to start, but one good way to start this is to start with just any of the graphs and see if you can identify whether its derivative is on there. Okay, so for instance, if I look at the red graph here, the red graph looks like it has a horizontal tangent line somewhere about right here, and so its derivative would have to be 0, and it looks like b is 0 at that point, so that's reasonable. So b might be the derivative of a, but I'm not done, gathering evidence. So let's see what else is happening here. A is decreasing after that point, and b is negative, so further evidence to support this. A is increasing before all the way through to here, and b is positive all the way through there, so that's more evidence Notice that right through here that A is concave up and B is increasing, and then A goes to concave down and B starts to decrease. So all of those things kind of indicate that B is the derivative of A. So I'm going to write over here A prime is equal to B. Now what about C? Um, Notice that B is a horizontal tangent line right here, and C goes through the x-axis. So that helps out with that. Um, it looks like B goes horizontal again somewhere over here. Notice that C goes through 0 somewhere in here. It's a little hard to see, but that seems to be the case. When B is increasing, C is positive. When B is decreasing, C is negative. And then through here, it's kind of hard to tell what's going on. It looks like it's essentially 0 most of the time through there. Also, when B is concave up, C is increasing, then B goes concave down, C is decreasing, and then B goes concave up again and C starts to increase. So it looks like B prime is equal to C. But that means B prime is A double prime, so that should be enough for you to determine which one's F, F prime, and F double prime. Make sure you include reasoning with your work or it is incomplete. All right, go study.